Here we see a heating curve. Notice heating curves are graphs of temperature over time as heat is being added. Now, I like this heating curve because not only does it give you the heating curve shape that you'll see the characteristic shape of the heating curve, but also you're going to see that up here above, you see that on the molecular level, the behavior of the matter. So if this is for water, so here you see it's a solid. Notice you see here there's a mixture. This is where your phase change is taking place. You have a little bit of solid and a little bit of liquid. Then you have just a liquid phase. Here you see you have a little bit of liquid and a little bit of gas. And then in this region, it's just a gas. So this corresponds to each part of this heating curve. So let me explain to you, looking at our notes, the parts of the heating curve and how it's defined. So heating curves are graphs of temperature versus time of a substance being gradually heated or cooled. Now here we're looking at a heating curve because you can tell that over time that the temperature is increasing. That means you're heating it. A cooling curve would basically have the same characteristic shape, but it would start off at a very high temperature and it would come down, plateau, come down again, plateau, and then come down again as you cooled it over time. But for our notes, we're going to look at a heating curve. I want you to notice here, and I'm going to clarify on my chart here. Point A, I've got A, B, C, D, E, F. A is representing this point. B is representing this point. C, D, E, and F. All right, so let's talk about what state of matter is present at each point on the heating curve. So between A and B, this is when the substance would be really, really cold. Notice the temperature increases as you go up. So here, this is your very cold temperatures. So just for reference, this is just arbitrary numbers. Let's just say this represents negative 20 degrees Celsius. So super cold. So if this were water, if we started heating a piece of ice that was at negative 20 degrees Celsius, it would be, since it's ice, in the solid state. So from between A and B, we have just a solid. Now, as the temperature increases, it's still a solid until it hits point B. So for water, if this were water, this would correspond here to the melting point of water, also known as the freezing point of water, which is 0 degrees Celsius. So this is the point that the substance starts to undergo a phase change. So this is a plateau. The flat regions on your heating curve is where the phase changes are taking place. So between B and C, you're going to have a solid in equilibrium with a liquid. That's where melting is occurring. Okay. All right, so as you continue to heat it, notice this, the graph stays flat in this plateau region because that's what happens during the phase change. During the phase changes, all of the energy is going to separate the molecules so the phase change can take place, and that's why you don't see an increase in temperature. But as soon as the last little tiny piece of solid ice has melted, then you will notice the temperature will start to rise pretty rapidly here over time. So between C and D, you have just a liquid. Finally, as you continue heating, eventually it'll reach the boiling point. So that's where the next phase change takes place. Notice you have a plateau, it flattens out again. So for water here, I'm just going to put again for reference, let's say this will be 100 degrees Celsius for water. That's where point D corresponds to. So between D and E, you have a liquid in equilibrium with a gas. And that's where we would call that boiling, or if you were just letting it happen at a room temperature, we call it evaporation, but we'll call it boiling here. Okay. All right. Once the last little piece of liquid is gone and everything is a vapor, the temperature starts to rise again. And so between E and F, we only have the gas phase. Now, one thing I do want to point out here about the two plateaus, there are always going to be two plateau regions for water. So the plateau regions are these flat regions. I'm going to highlight it here. And one thing that will always be true if you compare the two plateaus here, the plateau where the liquid is changing to a vapor is always going to be a longer plateau, or it's going to take more time. It takes more time for that to happen. And it's because it takes more energy to change a liquid to a gas, which is what's going on here, than to change the solid to the liquid. That's why this is a shorter time. It doesn't take as much energy or as much time. So that's the reason this plateau is always the longest plateau. You got to separate those molecules farther apart in order for that phase change to occur. A couple of side notes about your heating and cooling curve. The plateau regions, these are the horizontal lines on the graph that I just highlighted. This is your phase change region. There will be two phase change regions on the graph for water and most substances. Now, one thing that's really important to understand, so I would highlight this in your notes, during the plateau region, during this time, all of the energy that is added is used only to separate the molecules for the phase change. That's why the temperature does not increase. And that's why very little energy appears as kinetic energy. Now, the energy that is used to separate the molecules for each phase change has a very special name. One of them is called heat of fusion, and the other is called heat of vaporization. Let's define these. Heat of fusion is the energy used during the phase change of the solid to the liquid or the liquid to the solid. I remember fusion means they're coming together, and the only state that has the atoms held in place or held together is the solid. So the heat of fusion is going to be involved there where there's a solid and a liquid. On the graph, that was region B to C. So we'll go back on the graph and label that in just a second. Then you have the heat of vaporization. Notice you see the word vapor here, meaning gas is present. Heat of vaporization is the energy used during the phase change of the liquid changing to the gas or the gas changing to the liquid. And on your diagram that we just looked at, we'll go back in a second, label this one too. That was between points D and E on your graph. A couple of other things I want to point out about your heating curve. If you refer back to the graph we just looked at on the previous slide, the melting point is going to be considered point B on your graph. The freezing point is point C on your graph, and the boiling point is point D on your graph. So let's go back and label those few things I just mentioned to finish this lesson up. So the energy used during this phase change, this is called the heat of fusion. Okay, that's the energy between here and here. The energy used to go to the vapor state, the energy used and focused on separating the molecules here is called the heat of vaporization, and the symbol is delta H, VAP. All right. And finally, let's label a few of the points. I said that the melting point on your graph is point B. So this is considered the melting point. Because that's when the solid would start to melt.